It's a balanced beam with two heavy masses at different locations. Let's say that this mass on the left is, let's say, 50 kilograms. This one can be like 120 kilograms. Okay. Alright, so we've got an FG of mass A here and an FG of mass B. We want to know what those forces are, so let's calculate them. FGA is 50 kilograms times G. That's 490 newtons. And then over here, FGB will be 120, 9.8, and that makes 1176 newtons. The beam itself has mass, but the beam's center of mass, of course, is at pivot point P. So the beam can't exert any torque. It wouldn't make the system want to angularly accelerate. Like if those masses weren't there, it would be just perfectly balanced. It wouldn't rotate. So when we go to find what's called the net torque, we want to just sum up the torque due to A and the torque due to B and the torque due to the beam, but that's just 0. Alright, so how do we find these exactly? Well, it's a problem that's two-dimensional. Alright, so we can find the net torque with respect to the z-axis. Alright, that's into and out of the page. So for A, we'll have RA times the force at A. Okay, but we have to decide whether that's going to be positive or negative. A would make our beam want to angularly accelerate the positive direction. So this one can stay positive. For B, though, it alone would make our beam want to angularly accelerate clockwise, so we have to make that a negative. So minus RB FGB. And then for our beam, it's just 0. Alright, let's see what we can do. Our R vectors point from the pivot point to where the force is applied. That's RA. And this is RB. Torque is a cross product between R and the force. But here they're 90 degrees with each other, so we don't have to use the sine of an angle. Otherwise I would have put that on there, but here the angle between them is 90, so you get the full magnitude of the torque here. So 2 meters, 490 newtons, minus 1 meter, 1176 newtons. And it's like, which one wins, right? Like, does this thing end up wanting to angularly accelerate clockwise or counterclockwise? It's clockwise, right? This one has a larger torque. Final torque is negative 196 newton meters. Yeah, and that would be clockwise. Clockwise net torque. Next, we want to go on to find this beam's initial magnitude of angular acceleration when it's in the position shown. So now we want to use what's called Newton's second law for rotation. And the way that works is, instead of saying that the sum of the forces equals MA, we're going to say that the sum of the torques equals I alpha. Alright, so this is the net torque on the left. This is the moment of inertia here. And this is, of course, the angular acceleration. When it comes to these quantities, we want to plug in our quantities. We could do it with respect to the z-axis, which means we can put in a positive or negative. So put a negative 196 Newton meter torque here. And we have to calculate the moment of inertia of the system. I don't know what it is yet. We got to find it. So how do you do that? Well, you have to look at the types of objects involved. Moment of inertia is quite a bit more complicated than just calculating a mass. Here, we have to sum up the moment of inertias of the different objects involved, and they have different formulas. So, a ball like this could be treated as what's called a point mass. Means all its mass is basically concentrated in one location for the most part. So that's what we'll treat it as if it was just a dot of mass. These point masses have the formula for moment of inertia of mr squared, where m is the mass, r is the distance to the pivot point. So for our point masses, we're going to have, let's see, 50 kilograms times 2 meters squared. That's going to be one of them. So the mass of the 50 times the r of the 50 squared. And then you got the mass of the 120 times the r of the 120 squared. That'll take care of the two balls that are involved. But now we need a moment of inertia of even the beam itself. There are tables of just moment of inertia formulas for different geometries. And it actually matters where the thing is hinged too, like where the pivot point is. So if you have a rod like this, and let's say the axis of rotation is going to be right through the middle, like that's what we have in our case. There's one formula for that. But if you have a rod where it's actually spinning about one end, where that's the axis of rotation, then it has a different formula. So let's look up on the tables what the formulas are for these different cases. Okay, so if you look here, we can see that a particle of mass m has the moment of inertia mr squared, even if that particle is moving and following some kind of orbit. It has the same formula. But what we're talking about for the beam would be a thin rod of length L that's rotating about center. That would be 1/12 ml squared. If it were rotating about one end, the moment of inertia formula would be different. It would be 1/3 ml squared. So that's something to watch for. Alright, so here we have 1/12 ml squared, where L is the length of the beam. Here we'd have 1/3 ml squared. So the moment of inertia is larger in this case because more of the mass is concentrated away from the axis of rotation. It just means it's more difficult to get the thing spinning around that big loop. Here, a lot of the mass is concentrated in the center, so we have a smaller moment of inertia. It's easier to get it to accelerate angularly. And that'll be our formula. Alright, so let's plug in here. We'll get negative 196. We're going to have 50 kilograms times 2 meters squared. Alright, that's for this ball on the left. We're going to need another parenthesis here. Okay, then we'll put in the 120. And its distance is 1 meter from pivot point. Then we'll do 1/12 mass of the beam. We'll have to find that. And the length of the beam is 6 meters. Alright, so the length, 6 meters. We have to find the mass. Let's use that old formula. Linear mass density times L. Alright, so the mass of the beam, 10 kilograms per meter times 6 meters. It's 60 kilograms. Alright, so now let's plug that in. 60 kilograms, 6 meters squared times alpha. Alright, we'll see what contribution each of the objects gives towards the moment of inertia. See, this is going to be 200 kilogram meters squared will be the units of moment of inertia. Over here we'll have 120 kilogram meters squared, and then it looks like 180 kilogram meters squared. Now, moment of inertia is just a scalar, not a vector. And it just tells us about the resistance to angular acceleration. So there's quite a bit of resistance contributed by the beam itself, 180 there. The most resistance actually comes from, believe it or not, the point mass here. Why? Because it's so far away from pivot point P. It's difficult to get that thing to go all the way around, you know. So that's the reasoning there. It's a total moment of inertia though. 200 plus 120 plus 180 makes, I guess, 500 kilogram meters squared. Looks like our alpha is 0.392. Units will be radians per second squared. It will be negative, which means clockwise angular acceleration.